Alright, listen up, you primitive screwheads. Engineers. When you're rolling across a bridge in a Rolls Royce or a turd of a car, since you're still broke from attending UTD, you wouldn't want that bridge to collapse now, would you? So engineers make sure this doesn't happen by using math and science to design trusses and supports that'll help keep a bridge stay upright so that precious cargo can get across.
What type of math is used for these types of calculations, you might ask? Well. That would be quantum mechanics. Ha! Just kidding. It'll be the one and only linear algebra. Linear algebra is actually used quite heavily in structural engineering and a lot of mechanical engineering, so basically, it's a big part of our everyday lives.
As anyone who's played with a tape measure would know, the further a piece of material is extended, the more it wants to bend, collapse, and fold. Thus, a bridge spanning a creek or the mighty Mississippi will need supports in the form of pillars, trusses, and suspension structures. The forces experienced by the joints and members of a bridge's skeleton must be calculated to ensure the material isn't overloaded. So pay attention, you soon-to-be mechanical engineers.
Let's start the basis. When you build a bridge, the sum of the forces must equal to 0 so that the structure is in equilibrium, aka not wobbly and not a death trap or something like that. So what are these forces, you ask? Well, they are compression and tension stresses along the structural bits, which are the members, and the torque and weight or the load on the joints that connect the bridge to the ground.
As you can see from the great bridges around the world, bridges have a lot of trusses or suspension members and cables supporting them, and they usually have a lot of unknown forces acting upon them, like the wind, earth movements, or various vehicles and people. Each truss and joint needs a sum of force equation with variables for load in the horizontal, vertical, and any angle in between that's acting on them at any given time.
Also, there are basically an infinite amount of truss designs. Everything depends on what your specific need for the truss is, like moving boxes from one side of a cliff to another. So how do you solve a giant system of equations with countless variables? Use a matrix, of course. And here's Eric with something that may or may not involve matrices.
This game is about building bridges. Here's life without linear algebra. And as you can see, there might be some value to learning the subject, especially when dealing with hardcore stresses like getting an elephant across a bridge to your window. This is showing the stresses that are being put on the beams. And you don't want the strength of your bridge to succumb to the stresses of everyday life. And elephants being pushed about it, of course. There are many uses of linear algebra within truss systems. One is to find when the system will fail under pressure, the forces on the member, and displacement of the truss. All of these processes are nowadays solved through MATLAB or other software. We can also figure out these values by hand if necessary, however, a tedious and long process. There is a limit on how many members you can have, and that is restrained by the amount of joints in the system. For example, if there are 4 joints, there will be 8 equations of static equilibrium. If there are too many members or too little joints in the system, there will be problems with solving an unsolvable problem. You will either have too many solutions or no solutions at all.
Alright, that may or may not have demonstrated how to solve a truss with skills from linear algebra. Thank you for watching. However, disclaimer, this video will not make you a bridge engineer, so don't go freelancing for a construction company. You really don't want to get involved with a class action lawsuit, especially if death is involved. Thank you.